Greetings, everyone. It's our pleasure to present for you our thesis journey today. Me, Sarah Ali, and my colleagues, Ashrakat Elkhalifa, Mariam Mousa, Nouran Abdelaziz, Nada Badawy, and Eman Darwish. First, we'll start with our outline. First, we'll start with our motivation, the problem definition, our solution, and then the methodology that we used, and finally, our empowerment outcome. Okay, before starting our journey, we need to introduce a very hot topic and trending industry, which is IoT, which stands for the Internet of Things. It's a very growing industry. A simple example for it is smart houses, where everything can be controlled and connected by your phone. It's a very growing industry, as we can see, 8 billion IoT connected devices utilized by 2022, and this number is expected to increase to 24 billion. Alongside IoT, there's another hot and trending industry, which is machine learning and artificial intelligence. As we can see, 45% of the global market of machine learning is expected to increase by 2020, and 27% of the IoT devices that has AI on top of it are expected to increase by 2026. The reason is the merging between AI and IoT allow for increase of the operational efficiency, smarter application, and it enhance the protective and the autonomous applications.
Training machine learning models needs a lot of large data set that needs large space and high computation power. Also, the size of the model produced has very large size, which need large space and area. Therefore, machine learning models are run on the cloud due to the presence of high computing power and large space. However, there are some cons of running on cloud, such as transmission delays, as we wait for the data to be sent to the cloud, being predicted there in the model, and then the result is sent back to us. In addition to the high energy cost and the security and privacy issues we face in the cloud. So they were thinking of running machine learning models from being on cloud to being on edge. So that we can have less latency, more reliability, and less energy consumption. However, edge have some limitations, such as in memory constraints and low computation power. So the problem is now that we cannot deploy the machine learning models as they are with their large computation power and large space on the limited edge device. So we first need to optimize the model to be able to deploy them and do the inference there. And this is what is TinyML all about.
And since these ML applications need to communicate frequently with the cloud and other IoT devices, we need to secure these communications because they can be used by attackers as an entry point to our system. Hence, these communications are secured using HTTPS instead of HTTP.
Although there were many attempts to reduce the computations and reduce the machine learning model size in the software side in order to be deployed on the edge, it still needs a high processing power, and it still needs a high processing power in order to meet the timing constraints. To make the problem clearer, let's take keyword spotting application as an example, where someone says a command and the device should capture the keywords from the audio and do an action based on it. Let's say that the time between two audio frames is 25 milliseconds, and assume that the program clock cycles is 5 million. If we choose a clock frequency of 100 megahertz, then the power consumption would be X, for example. But then given the 5 million clock cycles, we would have an execution time of 50 milliseconds, which means that the deadline will be missed. The first solution that would come to our mind is to double the clock frequency. However, this would also double the power consumption. In the ideal scenario, we'd want to use the same clock frequency and eventually the same power consumption and meet the deadline. But what is the problem of having high power consumption? High power consumption is usually associated with high cost and short battery life. And usually IoT devices need a long battery life because in many situations, it's very difficult or even impossible to change the battery frequently. So our problem became to design a ready-to-fabricate secured IoT edge SoC with machine learning capabilities, which meets the timing constraints of real-time applications while consuming the lowest power.
So, in order to solve this problem, we propose a hardware-software co-design solution in which we investigate both the software and the hardware components, and we are trying to migrate the bottlenecks in the software program to hardware level. So to reach at the end to deploy machine learning models on the accelerated and secure open source system on a chip for IoT applications. So, however, this solution encounters many challenges. For example, if we want to design and fabricate an open source system on a chip, we will need RTL design and the ADA tools and the BDK to all be open source. However, RTL designs and ADA tools have recently some open source we can find, but BDK we need an open source process for that. And also one another problem is that the fabrication has high cost. So recently, after releasing Sky 130 technology, it released our problems. Hence, the Sky 130 is an open source BDK. And also, the second problem is solved by Google-sponsored MBW shuttle, which supports the open source technologies and the system on a chip to be fabricated freely. So, these encourage us to design ready to fabricate and SoCs an SoC with 2 extra hardware components, one for the data security and the other for the machine learning models. And here we reached 1.5 speed up for the 2 acceleration, and that was great. And we did that by okay. So our solution starts with choosing the base SoC for our model. Then we design the hardware accelerator for security, and then support it with the software components. And we did the same methodology with the machine learning accelerator, and then we integrate both accelerators to the base SoC, and finally we harden all of them. So let's start by choosing our base SoC. So we choose the Chameleon SoC to be our base SoC, and we choose it because it's an open source and it's designed by AUC Open Source Hardware Lab. We choose it also because it has peripherals that communicate with other devices, and also has one core which serve perfectly for our purpose, which is the base for the another components. Then after choosing our base SoC, we want to make sure that the SoC is working and all peripherals are working good. So some peripherals were already tested, but we also added some test cases for another peripherals like I2C or SPI2, and also we test some of the interrupts. And we did that by linking the C code, which have the test cases with the drivers and registers, and compile it with the RISC-32V compiler toolchain, and we took the hex file, outputted from it to put it in the simulation test bench, which we will be loaded to the flash and then execute on our SoC. And here our results for that showed that all tests are passed. And now we will, after verifying our SOC, we will be ready to go to design our the main components, which are the accelerators. Okay.
Okay, so the methodology that we use to design the accelerators is as follows. First, we choose the libraries that will be used as an interface to our accelerators. Second, we profile those libraries to identify the bottlenecks, which are the functions that took the greatest amount of time. And finally, we migrate those functions from software to hardware to implement them as our accelerators. So starting with the security accelerator, the library that we choose is Wolf SSL. It's a lightweight C library that implements the SSL protocol, which is used in HTTPS. This library is mainly used for embedded devices, and some of its features are full client and server support, a list of supported ciphers, and key and certificate generation. So the second step in our methodology is to profile the library. And the profiling revealed to us that the function that took the most time is the Montgomery reduction algorithm, which calculates the following formula: X times R inverse mod N.
This is our design implementation. As we can see here, we obtained a pipeline design to reuse hardware to reuse hardware components to further optimize our solution. So we are not only reducing the time from by migrating from the software to the hardware, but we also are reducing and optimizing the area. So as we can see, this design only consumes 7% of the gate count and almost 6% of the area of the entire SOC. And after testing this design, we obtained almost a 50% acceleration, which what we aimed for.
And now for the third part, which is the second component, which is the machine learning accelerator. As Mariam mentioned before, we decide the model and then we try to find the bottleneck. So we decided to work on the NNOM library. Why NNOM especially? Because NNOM supports in complex models like Inception and ResNet, and that's because it uses Keras models and then converts it into the NNOM, and then it can be used. The second more thing is that it's lightweight, user-friendly, and flexible to use with high performance considering the NN library, which made it perfect to use and analyze because it supports also microcontrollers. So we started to find the bottlenecks by profiling. So we found out the convolution function itself utilizes up to 95% of the NNOM library of the execution time. So that took our focus. So we started to analyze these results and we found out the multiply and accumulation operation consumes up to 41% of the execution time, and the memory access utilizes 58%. So we started to build our building unit of this accelerator by designing the MAC operator. So the basic model, the difference between the basic model here and our unit is that the basic model by every cycle, it uploads 32-bit and uses it and output the result directly. But we are here utilizing the fact that parallelism makes things faster. So we are operating in each unit 8-bit at a time, each bit paralleling, which will output the 32-bit with 4 units, which is faster and more efficient to use.
We also thought of making use of the properties of convolution, such as parallelism and reusing of input data. So for instance, in this example, as you see, we have 2 filters. They are convolved with the input pixels to produce the feature output map. These 2 operations are actually independent of each other. They can happen in parallel. so we can further accelerate our speed up. Moreover, we can make use of reusing the input data. So just have the memory access just once instead of reading them twice for each filter. And thus our accelerator was composed of 4 parallel paths, each path for a filter, and each unit format is composed of the unit that just Eman was explaining. Our accelerator has a gate count of 4.7% of the total accelerator and an area of 3.7% of the total area of the SoC. We then move to the software adjustment of the NNM library. So we understand the convolution code very well, understanding memory storage of input data, and then modify the convolution code of NNM library in order to accommodate our accelerator. And finally, we were able to test our accelerator in an SoC, and we were able to achieve an acceleration of 34.8% when testing with 2 filters and 51.4% when testing with 4 filters. We also migrated TAN-H and sigmoid activation function lookup table from being on software to hardware in order to reduce the on-chip memory. So each of TAN-H and sigmoid, number of gates is about 200, which save each 2048 bits from being stored on the on-chip memory.
After we're done with designing our accelerators, we needed to integrate them with our Chameleon SoC. To do this, we made the accelerators act as a slave on the high-speed bus, and we supported this in the software by loading their inputs using a certain base address for each accelerator in order for the bus to recognize them. After we're done with our SoC, we needed to validate it. However, if we go through the fabrication process, it takes too long, and once we do the fabrication, we cannot change anything in the hardware. So we validated our FPGA using the CMOD Arctic 7 FPGA board, but we faced the problem of how are we going to load our program into the SoC. To solve this problem, we added a read-only memory slave on the bus, and we loaded the program into it, and we changed the boot address of IBEX to fetch from the ROM instead of the flash. And we wrote a C program which toggles the GPI open, and it's connected to the LED in order to test this, and here's the result. However, this solution has a limitation because once we load the program into the SoC, we cannot erase it and load a new one. So we modified our design to include a flash writer, which will be also a slave on the bus, and it includes as well a UART master, in which we will use to program the flash writer, and we also added a master multiplexer, which will multiplex between the 2 masters, the UART and the IBEX core. And once the program is loaded into the flash, IBEX will be able to fetch the instructions normally from the flash using the quad SPI controller. So as you can see in the diagram and the picture, we will have the Python code, the Python script running on the PC, and a USB TTL module will be connected to it, and it will be connected to the SoC as well, specifically the UART master, and the flash module will be connected to the SoC, specifically the flash writer. And we also wrote a Python script to support this. And here's the software stack of our code. We at first use the commands of the flash in order to program it, and we send this using the SPI protocol, and then we go through the AHB bus protocol in order to program the flash writer, and then finally we use the UART protocol in order to communicate with the UART master through the transmit and receive signals.
And now the final part, after we finished everything, we did the designing and verifying, and now it's part time for hardening. So we used the OpenLane and Sky 130 technology to harden our SoC, and that by giving it the sources, and it uses the ASIC flow to convert the RTL into the GDS file, which will be used this is the GDS file. It's a software explanation for the hardening of the SoC, and it's consuming 0.6 millimeter square area and with clock frequency of 33 megahertz. So after that, after we got the GDS, it's now time to put it into the vanilla Caravelle, which is something like a layout to put our user project wrapper in it. And that will be the final project, the final output that will be sent to the shuttle. It will be something like that. Like that, our final product. So you can take a hint. And after that, we will send it to Google Shuttle mid-June, we aim for. And that's it for our empowerment outcome. We had contributed to an NOM project, which is the library we mentioned before. And we have an open source so that any common projects that need to work after us can use it. It's totally open source, and you can scan the QR code here. And for the documentation, we're working nowadays on a paper, and we try to publish it soon. And that was it. I'd like to thank our family and friends for all the love and support, and we like to thank the commitment, and special thanks to Dr. Shalan, our supervisor. It couldn't be done without him. Thank you.